We often investigate networks to understand how they are built, or how they behave, and even how to predict their behavior. But our ultimate goal is to influence their behavior. Let's begin with an example. Here is a nonlinear dynamics model for gene regulation. It follows the activation interactions between genes in a cellular network. As you can see, it combines the network structure, but also the nonlinear interaction dynamics that take place on the network. This is how this system behaves. Put it at a high initial condition, and it converges to a high active state. Put it at a low initial condition, and it converges to 0. It was shown that the full solution of this set of equations is the following. Y-axis is the average activity. X-axis is the connectivity captured by the product of the average weight and the average degree. Actually, it is the average degree of a neighbor, but this belongs in another talk. Here you see the active state in green. All genes are busy and active, and the cell thrives. The low active state is when all activities vanish and the cell dies. Suppose a system begins at the active state. Then, due to a series of damages to the connections, lost nodes or links, the system collapses and transitions to the inactive state. How do we revive it? Well, you would think that the best thing to do is restore the lost connections to bring the network back to its original structure. However, unfortunately, we find that this is not enough. The system stays inactive. It doesn't spontaneously revive its lost dynamics. So what can we do? We have to reignite the dynamics of the system, kickstart it to push it back into activity. If we can pull up the activity of all of the nodes, of course it would help, but we almost never have this level of control. So the question is, can we revive the system by controlling just a single node? To answer this, we discovered a new dynamic phase of the system. In the red regime, where the weight and degree are small, the system is in the inactive phase, but we already knew that. In the yellow area, the system can be active, but it does not revive on its own. But we already knew that. But in the blue area, we found that there is a new state of the system, the recoverable phase. If we can just control one single node, see what happens. The controlled node impacts its neighbors, its next neighbors, and so on, until all the entire network transitions to the active state. Now we can just let it be, release our intervention, and the system stays at its new state. It has been reignited. So to recap, how do you revive a failed network? You do it in 2 steps. First, you restructure your network, bring it into the blue recoverable phase. Then, once in the recoverable phase, you reignite its dynamics with just one or few nodes. Is this only for gene regulation? Certainly not. Here you see how we kickstart a collapsed microbiome. First, we add nutrients to impact the network structure, for example, to reduce a competitive link or to enhance a cooperative connection. Then, using probiotics, we control a single microbial species. The result? The system recovers and gradually goes back to its active and happy state. So yes, we can use our networks to create a macroscopic change in the system's behavior with just a local microscopic intervention. I want to thank my collaborators, Jianxi Gao, Amir Bashan, Moshe Schwartz, Shlomo Avlin, and Baruch Barzel. And thank you for listening.